Welcome to our numerical analysis presentation over the interpolation of audio waveforms. I'm Riddock Moran.
And I am Michael Rahe.
And we are from the School of Computing at the University of Nebraska-Lincoln.
So to kind of go over what we'll be talking about in this presentation, we'll first go over the motivation of our project, and then we'll go over how we collected our data that we used, as well as issues that came along with that. And then we'll talk about the two methods that we ended up using, which in this case are piecewise linear interpolation and R-cubic interpolation. Then we'll look at the graphs that we were able to form off those MATLAB scripts, and then we'll do a little bit of a conclusion and wrap up with future work. So the motivation. Riddock and I are currently involved in a senior design class or project that involves making a function generator and oscilloscope with a mobile app. In order to display the values from the mobile app, we're going to need to find some sort of way to interpolate the values that are being brought on from the phone. So our idea was to instead of pulling so many samples from the phone at one time, we could use interpolation to estimate what the values in between were to save some computational cycles, as well as smooth out different points on our graphs.
And as far as data collection, we used an Arduino Nano board. So we just took in an analog in that was connected to an audio jack. And it was just playing different signals. The one that we used the most was the 440 hertz sine wave. And a couple issues with how we collected our data was we were hoping for a 48 kilohertz sampling rate, but because the analog read has a delay of around 112 microseconds, the highest sampling rate we could achieve was around 8.9 kilohertz. And another issue that we ran into was we wanted to see what it would look like if we output the samples back to an oscilloscope, but the analog write uses pulse width modulation. So there's no way to actually get an analog value back out of the board.
So looking at our first method we used, which is piecewise linear interpolation, the equation that we use can be seen there at the top of the slide. This essentially just makes a linear approximation between two values. So essentially just a straight line. This could leave for a lot of room for error, potentially if, as we'll see later on, with high frequency waves, that the values might not necessarily always be a straight line, but it's coming back down when it oscillates.
And the second method that we used was a R-cubic spline interpolation. So similar to linear interpolation, this creates a function in between each pair of points, but in this case, it is a cubic function. And so you can see the formula at the top to find that cubic spline. And then there's a little snippet of the MATLAB code that we use to find the cubic splines.
So here we can look at the two methods being used to interpolate over what was a 440 hertz sine that was being outputted on the board. If you look at the top middle of the piecewise linear, you can see that they are straight lines that can kind of be pretty rough when we know that a sine wave is pretty smooth as it's going around on the curve. But if we look to the right here on the R-cubic spline, it's very evident that the spline function does an excellent job of smoothing out the curves as the values move on. Look at this. This is the 1000 hertz sine wave. And so in here we see the issue that I had previously mentioned about as higher frequencies come about with the board, it's harder to interpolate on that because of the oscillation. It's harder to predict what the values are because of how close the values are to each other and how fast it's oscillating up and down. Both of them have generally the same shape, which is a positive for both our methods, but not in practical use in terms of what the actual wave being outputted is. But once again, R-cubic spline wins out here to show a much smoother curve. Then here is our final set of graphs showing off a 440 hertz triangle wave. Same deal as the previous ones. The piecewise linear has straight lines for every point, whereas with the cubic spline it has a much smoother edges, but both equally have very good interpolated values.
And so this is a screen cap of our audio wave put directly onto an oscilloscope. So you can see the 440 sine waveform. And so we wanted to find a function that approximately matched this. And so that's the function that we have there. And this function matches our samples with an RMS error of about 0.0315. And so it's a pretty good match. And so this is the function that we compare our interpolations to. And so if we didn't use any interpolation, we would get an RMS error of 0.1419. So pretty high relative to what our interpolation is going to be. Here's the piecewise linear, and it does a really good job when you're just visually comparing these two. And that's a RMS error of 0.0314. And then the R cubic spline, again, it does a really good job visually, and you can see it's even smoother than the linear, and at an equal error RMS error.
So to wrap things up, both of our methods did a pretty good job of smoothing out our errors and predicting the interpolation between different points. I think when it comes to recommending one, in our case, we're most likely going to go with a piecewise linear function on the account of it's very quick to implement. And for the general increase of RMS, we saw on the previous two slides that there was no difference. But in overall, the R cubic spline was better in terms of having a very smooth curve across the board.
And if we were to do this project again, we would want to use a better form of data collection, something that can give us more precise values and able to better represent higher frequencies, and possibly a board that you'd be able to actually run R cubic spline directly on the board.
And then the last thing for future work, we could potentially look at doing bilinear and bicubic. This would give us a better averaging between values, and hopefully for when it comes to higher frequency waves, this would better account for the faster oscillation and maybe giving us a better prediction of the values.
Great. Thank you for taking your time to watch our presentation.
Thank you.